this NARS tutorial. This tutorial will consist of two parts. I'm Wang. I'm going to give the first part, which is the conceptual design of the system. And after that, Patrick Hammer of the Open-NARS team, as well as helped by the other team members, is going to introduce the code to you. The material, I want to mention, first, this PowerPoint presentation is already linked to the conference schedule here. Okay. Probably slightly different from what I'm going to show, but it's basically the same thing. For the conceptual design, most of the stuff we are going to talk about today already published, can be accessed from my website. The easiest way to get here is just Google my name, and then you go to my website at Temple University, then you follow this publication link. There are about 60 papers on different aspects of this project. And also there are 2 books, which are unfortunately not online, but all the other papers are there. And then Patrick will mention the material, the documentation and so on of the code. So let's start from the very beginning. It's well known that a lot of difference in the field is caused by a different understanding about the concept of intelligence. So to mainstream AI, intelligence is typically interpreted as a collection of problem-specific and domain-specific functions. For AGI people, they typically take intelligence as a general purpose capability, and they should be treated as a whole. Even though that's more or less the consensus of the AGI community, we still actually define our task of research very differently. As you probably have already seen, if you haven't, you will see it in the next 3 days. So I will start with our understanding. So the whole work, a lot of discussion will go back to this very paragraph. That is, intelligence in our work is understood or interpreted as the capability of a system to adapt to its environment and to work with insufficient knowledge and resources. So there are 2 components in this working definition or our understanding of intelligence. One is adaptation, which is not very controversial. Right? I think most people agree. But the other one is probably the one that actually distinguishes our work from many other works in the field. That is a so-called assumption of insufficient knowledge and resources, sometimes referred to as AIKR. What does that mean? That actually means 3 things. One is to rely on finite processing power in terms of, say, number of processors, processor speed, the amount of storage capacity, and so on. Okay? You have a finite amount. And second one is the system must work in real time. Actually, by real time, we mean something slightly different from the field. In the field of computer science, real time typically taken to mean something like you have a deadline, right? In our system, actually, we mean more than that. We mean for most of the tasks, the requirement is to solve it as soon as possible, with different levels of, a sense of pressure or urgency. Later we'll see more details. Okay? That's what we mean by real time. And finally, we want the system to be able to open to unexpected tasks. Roughly speaking, it means 2 things. Of course, every system can only perceive or accept tasks or new information in a certain format, that's for sure. Okay? But our definition requires that, yeah, you can say that there's a certain format you have to be in to be accepted by the system. But any content should be acceptable, which means several things. For example, it means new information can conflict with the system's current belief. The system cannot be killed by that, or crashed by that, or contradiction, or inconsistency will be allowed. Okay. Also, the new questions or new problems may be beyond the system's current capability, or beyond its current knowledge scope. You cannot just say, oh, I don't know. That's not something I have been designed to solve. Okay. The system has to try to work on those problems. That's what open means in this context. So that's very roughly speaking, at a very high level, philosophical level, what problem we want to solve. We want to build a system which satisfies this restriction. And then, on the technical side, the top level assumption or decision we make is to build a system in a framework of a reasoning system. Okay. This is not a new concept at all. I think everyone here, or almost everyone here, know what a reasoning system means in the field, which typically has the following components. It uses a formal language to represent its knowledge. It uses some kind of semantic theory to define what meaning and truth is on this language, so that we will understand how to use the language. Then there is a set of formal inference rules, okay, which derive new things from given things. And this array, typically put together, is called a logic, in the broad sense of the word. Then what? Then when we say we implement a logic into a system, we mean more than that. It's a logic plus something. That plus something includes at least a memory structure. Okay, we need to be able to remember the given knowledge and so on. And a control mechanism, which will decide in each step which promise to use and what inference rule to use. Those things put together is called reasoning systems. Yeah, very broad sense. So why to use a reasoning system? This is a controversial issue. Okay. I think many people now already think about, oh, reasoning system again, now this is already bad. Okay, now it's a neural network, which is the one that's promising. But I'm going to argue not only today, but also tomorrow and later, okay, whenever I have a chance, I will say, it's too early to say, okay? Reasoning systems still have some very important advantage compared to the other things, including neural network. One thing is it's domain independent. Okay, logic is not designed for any specific problem. That's easy to understand. And also, this is a little bit controversial. Many people say logic is too rigid. Okay, later I will show you when you extend it properly, a logic or a reasoning system can have a very rich expressing power. At least it should satisfy the requirement of AEI. And then another important feature is, you see, when you say your system is following a logic, that basically means every step you need to have a justification. Okay? An inference rule is not just a rule. It's a rule with a justification. Okay? It's something correct or valid to do. Not an arbitrary step. That's very important. But that sounds rigid. There is another aspect of a reasoning system is a flexibility. That is, even though each step needs to be justifiable, needs to be rigid, yes. But how you combine those steps together, it can be very flexible. So put together here, the vision is kind of intuitively speaking, something like we try to analyze all types of reasoning into basic steps, and we are going to define all those steps as an inference rule. And we are going to use their combination to reproduce all types of thinking process. Okay. That's kind of like the intuition. And let's see whether we can do it. But just from my previous description, some of you may have already seen a deep contradiction between what we want to do and how we try to achieve it. Why? Because under the assumption of insufficient knowledge and resource, it means what? It means there is no way for you to guarantee absolute correctness or absolute truth in your system. Okay? Everything can be challenged by future experiments, can be wrong in that sense. And also, you don't have enough time to go through all possibilities. So in this sense, everything will be uncertain. You will see, yes, that's indeed the case. On the other hand, logic traditionally is interpreted as a process which goes from truth to truth. If you have no truth to start with, and you cannot guarantee the truthfulness of your conclusion, how can you say you are following a logic? So there is actually a philosophical contradiction between our two assumptions, okay, our goal and our strategy. So the solution to that also is philosophical. Is I have tried, with the help of some other people, to redefine or reinterpret the concept of valid, what is valid or what is rational, on the foundation of available knowledge and resource. I will say that my conclusions are valid with respect to or relative to what I know and what resource I have at the moment. So that's the basic idea. So you see, I have already given up absolute truth or absolute optimum. In return, what I try to obtain is I want the system to be general, to be adaptive, to be flexible, and to be robust, and to be scalable. So that's kind of like the philosophical discussion. I don't want today to be pure philosophy. I know you don't want that. So, but I have to mention that because that's the foundation of everything else in the following. Okay? So from this slide, I'm going to begin to talk about technical stuff. But given the complexity of this project, there is absolutely no way for me to cover all or most of the technical material. I will just talk about the basic. Okay, for the rest, as I said, I have papers, I have books, and we have 3 more days. We will be here. Okay, otherwise, welcome to talk to me or to my team members about the details. But here I will talk about the basic. So, yeah, I said I use a formal logic, which means a formal language. This formal language, the smallest unit is what I call a term. A term is just, in the simplest form, it's just a word, okay? Or an ID, identifier within the system, which will be used as a name of a concept. Later I'm going to define what a concept means. But now we just use it intuitively. Then terms are related to each other to form statements. A statement in this system has a subject predicate format, and these two terms are related to each other by a copular. And see, formally, S is a subject term, P is a predicate term, this arrowhead is a copular I call inheritance. Intuitively speaking, it means the subject is a specialization of the predicate, and symmetrically, the predicate is a generalization of the subject. Concrete example, also you can put it in a graphical manner. Okay? You see each term is a node, and a copular is a link from the subject to the predicate. The direction matters. Okay? You see water is a type of liquid. So liquid is a more general concept compared to water. Water is a special case. So that's the intuitive meaning. And this copular, what I call inheritance, is formally defined by its two properties. One is reflexive, one is transitive. Reflexive means from every term, there is an inheritance relation to itself. Yes, water is water. Transitive means, well, if A is a type of B, B is a type of C, then A is a type of C. Well, it's trivially true. Okay. Then based on those trivial definitions, we can define first idealized truth value, that is a binary truth value, on the statement. First, we introduce the concept of experience to the system. Just like every reasoning system, you cannot get something from nothing, right? You have to start with some background knowledge or given premise, whatever you call it. In this system, it's called experience. Later, we'll see why. So it's just a set of given statements. Then based on that, I define the concept of the system's beliefs, which is the transitive closure of the experience. Intuitively speaking, that's basically what the system is told, as well as what can be derived from the given just by transitivity, okay, of the relationship. And there is only one relationship allowed at this stage, this inheritance. So you cannot be simple. What is true? Well, a statement is true. There are two situations. One is it's in the beliefs, which means it's either given or can be derived from the given. Or it's a tautology. That's true by definition. Otherwise, it's false. So here I'm using a closed or assumption, which is a common thing to do in AI as far as you say you only want a binary logic. So it's also pretty simple. Then we begin to define two new words, which use slightly differently compared to many other systems, even though the intuition is still there. I'm going to define extension and intension of a term. Formally speaking, the extension of a term, well, let me show you the picture, which shows it much better. Okay? So if T is any term here, its extension is a set of terms that there is an inheritance link from that term to T. That is, there are specializations. T's specializations, all the terms that's more special than T. Semantically, intension are the generalizations of T. That is, there is a link from T to those things. And T itself, by definition, is in its own extension and intension because of the reflexivity. Then there is a trivial but important theorem that can be proved. That is, there is an inheritance relation from S to T if and only if the extension of the subject is a subset of the extension of the predicate. If and only if the intention of the predicate is a subset of the intention of the subject. Okay, this is just transitivity. But why this is important? Because this is the foundation of extending this logic from a binary logic to a multi-valued logic. Okay. From my previous description, you should have already guessed. In this system, in my system, there is no absolute truth anymore. But on the other hand, I won't say everything is as good as everything else. So truth will be a matter of degree. Okay, just like many multi-value logic. But there is a common problem about multi-value logic, for example, fuzzy logic. That is what that number means. To make it very clear what that number means, what I'm doing, you see here, is I identify one of the statements I want to define on the left-hand side to the other two in the middle on the right-hand side, which are subset relations in set theory. I say they're the same thing. But a subset relation can be very naturally extended from binary to multi-value. Okay? A binary subset relation is basically saying, okay, A is a subset of B, means 100% of A is in B. If I want to make it 80%, everyone understands what I mean. Okay, 80% of A is in B, the other 20% are not. So in the following, I'm going to do my trick for this logic. So I'm going to piece by piece introduce what the evidence for a sentence to be said to be true, and what is the evidence for a statement to be said to be false. According to the previous theorem, okay, then you see it will naturally lead to a multi-valued logic with a clearly defined semantics, what that number means. So for a given statement, S is a type of B, I will say everything in a common subset, common extension or common intension of the two terms are positive evidence. Negative evidence are the terms that in the extension of the subject but not in the extension of the predicate, or in the intension of the predicate but not in the intention of the subject. Again, it sounds complicated. Let me show you the picture. So we're talking about this relation in the middle. If I can find something which is both in the extension of S and in the extension of P, as far as this thing is concerned, the extension of S is indeed included in the extension of P. Be careful here. I'm not talking about the whole extension. I'm talking about one instance of it. The same thing for intension. You see in the system, intension and extension are perfectly symmetric to each other. Okay? But for the negative evidence, if something is in here but not in here, of course, as far as this one is concerned, this subset relationship is not true anymore, which means equivalently, this inheritance relation is not true anymore. Okay? So based on that, not only I can define positive and negative, I can measure them. In a simplified situation, I simply just use the size of the set involved. So the amount of positive evidence means the size of the common extension and the common intention together. The total amount of negative evidence, is this part, or the kind of the red thing. You just count them, okay? That's negative. The green things are positive, and you get a total counting value. Okay? Then if you add them together, that's the total amount of evidence. According to what, of course, or according to the system's experience. Okay? Be careful. This is just the definition of evidence. This is not how it is actually calculated. That's a different story. Okay? Here, let's go back to see what we have done. First, we define what is experience. We use experience to define truth value. Then we use truth value to define extension and intention. Then eventually, we define for arbitrary statement. Given that experience, how much evidence you have, positive, negative for a given statement. Then finally, the last step, we use the amount of evidence to define truth value. What makes this system different is it's not only is a multi-value, it actually uses two numbers to represent the truth value. Okay? Many people say, oh, one number is already too complicated, you use two. Well, I have enough recently that I will show you. We use two numbers to represent a truth value. And both of them are real numbers between 0 and 1. The first number is called frequency. It should look very familiar. Is the proportion of positive evidence among all evidence. Like what I just said, okay, 80% support, 20% against. So frequency is 0.8. Okay? But be careful, this is not probability. Because probability is relative frequency take limit. Okay, I'm not taking limit. So it's just the current proportion of positive evidence among all evidence. And this evidence may come from extension, may come from intention, as I just defined. But still, this looks pretty natural. And the second component is probably most unique in terms of the semantics of the system, is what I call confidence. Okay? This same word has been used by several different theories like statistics to mean a slightly different thing. So here, what I use is for this W is the total amount of evidence divided by total amount of evidence plus 1. Y plus 1. Well, about story, okay, to make it short, actually it doesn't have to be plus 1. It can be plus 2 or 3 or 1. But the intuition is we need a measurement to measure how much you know about that thing. Okay? Traditional theory, including probability theory and fuzzy logic, have a problem of cannot really say, I don't know. You see, probability 0.5 doesn't mean I don't know. And here, we have a mechanism to really say, I have absolutely no idea. That is, confidence equal to 0. Okay. You see, this W is how much kind of like evidence you have seen. If you haven't seen anything, confidence is 0. If you have seen one piece of knowledge or one piece of evidence for that statement, you see, it's 1 divided by 2, it's 0.5. You have seen 2 of them is 2 divided by 3 is 2/3. And then it will be 3 divided by 4, 4 divided by 5. It will never reach 1. So basically, my current interpretation in my publication is basically say, what this measures is what you know at the moment compared to what you will know in the next moment after you get one piece of new evidence. Okay? So the next moment, you will always know more than the current moment because you get one piece more. But if you already know 1 million, and that difference will be very small. 1 million plus 1. Okay, is basically the same as 1 million. But 1 compared to 2, that's very different. So you see, the intuitive meaning of this measurement is to measure how the system will be sensitive to new evidence. The more you already know, the less sensitive it will be. But there is always a chance for you to get new evidence. So mathematically speaking, this formula actually indicates why I call my system non-axiomatic logic. That is, no absolute truth. Everything can be modified. It will become harder and harder and harder and harder if you get more and more and more and more evidence. Okay. So graphically speaking, then now we can add a weight value to the link. It just this weight value is actually 2 numbers as a pair. So now we can summarize the semantics of NARS, which is very unique. I say this system has an experience-grounded semantics in the sense that everything, semantically speaking, is defined with respect to the system's experience. So you see the truth value of a statement is defined by what? By available evidence. It's about how much you know about this thing. It's not defined with respect to a fact, which is traditionally how truth is defined in flexible model theory. Okay? True means match the reality. Here, there's no such a thing as reality. What you have is your experience. You compare your belief with your experience to see to what degree they fit into each other. The same thing about meaning. Traditionally, in model theoretic semantics, the meaning of a word is its reference in the world. Okay? There is an object where this term or this symbol is just the name of that object, and that object gives this symbol its meaning. No, that's not what this system does. This system, the meaning is what is defined by nothing but the extension and intension, which I just defined, of a term, which is the experience relation between that term and the other terms. So what this bottle means depends on how much I know about it. Okay? It doesn't really determine by what it really is. So it sounds simple, but if you think about it, there are several important implications which make the semantics fundamentally different from the semantics which is dominating the current research. First, you'll see both truth value and meaning are subjective. They're not objective. It depends on which system you're taking. Second, both of them change over time because what? Because experience, by definition, extend over time. Okay? A system always gets new experience, and those experiences, by definition, is going to change the meaning of the terms involved and the truth value of the statements involved. Okay? So objective or stable things, they're special cases. Changing things, subjective things, they are normal. They're the normal situation. And also objective is relatively speaking, or stable belief, yeah, you can have them, but they're relatively speaking. So this is very, very important. That's again the foundation of everything else. Of the following. Mm-hmm?
So if I understand right, would it be fair to say that NARS uses a procedural semantics rather than declarative one, where the meaning is based on the statements in which things occur, and the only kinds of statements your logic allows are specialization, generalization?
Not really. Well, it's related to later. I think I hope later I will explain the difference. But yes, there is some relation to what you said. Yes, but not exactly. Later we'll see it's not just specialization and generalization, and also not only procedural, and also it can be declarative. So that's how truth value are defined. Okay, how they're actually produced in the system. Of course, two sources. One is the input. Okay, the given you have to of course provide the initial truth value. By you, I mean the user or the designer. Okay. But it will be produced according to the semantics. For example, we're experimenting using existing knowledge source like WordNet, hook it up with NARS, and provide information to NARS. WordNet doesn't come with truth value at all. It's just binary. Well, we can use some default value. Okay? Or if you already have statistics, we can convert the statistics into truth value in a certain way. Okay? So it can come from somewhere. Also, all the inference rules later we'll see is going to take premise which is true to a degree, which will generate the conclusion of the cause is also true to a degree. Where those numbers come from? Well, they come from a bunch of truth value functions designed by the designer, but it's designed according to the semantics I just introduced. So you see, again, remember in the following, when we talk about truth value in NARS, don't think about the reality. Think about what the system knows about that thing. Okay, that's what this is all about. So truth function design, actually I also try to use probability theory in the first place because that's the most natural choice. But pretty soon I realized that it's not going to work. And so I use something else. Okay? The current approach is basically to treat the truth value in the system as an extension of Boolean matters. And Boolean value is just 0 or 1, right? We are going to treat 0 or 1 is an extreme case of the values I'm using, which is between 0 and 1. Okay, that's pretty natural. So we are going to start with Boolean value. Basically, we are going to study the boundary conditions first. So what if it's extreme, okay, 0 or 1? Then we are going to analyze the relationship between the premise and the conclusion according to the semantics I just introduced. Then we are going to build the Boolean functions among the variables involved, later we'll see an example. And finally, we are going to extend those Boolean values, Boolean functions, into real number functions. You'll see that Boolean functions basically are built by 3 operators, right? Not, and or. And I'm using this very simple treatment to extend them from Boolean to real number. Okay, those functions have been used by many systems, but with different semantic interpretation and justification, which in ours we are doing the same, but we interpret them differently, which I'm not going to talk about in detail today. Okay, you can see my publication for details. But anyway, let's see concrete example. The simplest rule is the deduction rule. You see, if M is a type of P to a degree, S is a type of M to a degree, then S is a type of P to a degree. This is nothing but transitivity extended from binary to multi-valued, right? So according to this analyze, I built the following function, which is first Boolean, then extended into truth value according to the way I mentioned. Okay. I'm not going to explain the detail why that's the case, but intuitively speaking, think about it, it makes sense. So this is a concrete example. You see that this 1 and 0.9 are the default truth value. If you tell the system something without saying anything specific about how true it is, the current default value is 100% positive. Confidence is 0.9. Why 0.9?